Cool. So let me turn on my camera for a second so people can see me. So first I want to thank the organizer for this opportunity. And today I'm going to tell you about the track reconstruction study we did under the framework of Athena detector proposal for EIC. And that is a collective effort. And we got a lot of help from the ACTS group. Okay, let me turn off the camera and continue. And oops, we can go to the next. Okay, cool. As many of you have heard, this Electron-Ion collider is approved to be built at Brookhaven National Lab. And with hadron beam energy of 100 of GeV and electron beam energy of 10 of GeV. And the crossing angle of the interaction will be 25 millirad, and the collision rate is expected to be below 1 megahertz, which is significantly lower than some of the high energy PP collisions. And with this kinematics, we were able to reach the center of mass energy as high as 140 GeV with a luminosity as large as 10 to the 34th. And we were hoping with this powerful machine, we will able to probe many interesting physics process, such as quark and gluon confinement, the proton spin puzzles, and the 3D image of proton and nucleon. So we are currently on the CD1 stage and still trying to decide a lot of the designs, including the detector, finalizing the detector designs, and the goal is to start operation in 2030. All right. So earlier last year, a call for Detector 1 proposal went out, and if you are interested in the details, you can look at the call for proposal page and also the Detector proposal advisory panel meeting indico page, which contains a lot of information for each of those proposals. And the goal is to select a reference design of Detector 1 that can meet all the physics requirements as identified in the EIC yellow report, and also address the concern of cost, schedule, and risk. So Athena, which will be my focus of this talk today, proposed to use a 3 Tesla new magnet. And you can see that within this solenoid magnet, we have a hybrid system of tracking, and then the parameters and the ridge detectors and so on. And then edge detector, which I will see share many similar configurations with Athena. The biggest difference is that they choose to reuse a 1.5 Tesla magnet from Barbar, which is currently being used by the S-Phoenix experiment. So actually it has been suggested as a reference design for Detector 1. And so in addition, we still have a third proposal, which is called Core. This is designed for interaction point 8. And which has a second focus, and that can be used for more far-forward physics. I think I forgot to mention that there are 2 possible locations to build the detectors, interaction point at the 6 o'clock and 8 o'clock location. And eventually, the decision was to build Detector 1 at IP6 location, which is more ready for construction. All right, let's now talk about Athena. So our tracking system are designed to be compact, low mass, and needs to have a large acceptance of eta to cover all the interesting physics. So here I'm showing you on the lower left our central hybrid tracking systems, and we also have a set of far-forward subsystems that we wanted to use to tag forward-going particles for many different physics processes, such as tagged pion structure function and deuteron offshore effect study. And to achieve those purposes, our final configuration of the Athena detector, Athena proposed tracking detector, has 3 vertex layer of silicons with the latest ITCS3 technology, and then you have 2 silicon barrels, and the outside of the silicon barrels you have the macro mega outer barrels. And to the electron going direction, you have 5 silicon disks, and also with the outer ring of gem detectors to expand the acceptance. To the hadron going direction, you have 6 silicon disks, and also a very large macro well disk behind the D-rich detector. And for the far-forward part, we will put a set of silicon disks inside the B0 beam magnet, and they can be used to track the charged particles. All right, so here I'm showing you schematics of the central detector system, which you can see how we integrated our tracking system inside the solenoid with other detector systems. And just wanted to give you an idea of the size of the detector. I think it's kind of small compared to other high energy physics detectors. And I just wanted to mention that we also have AC-LGAT and the calorimeter, which can provide tracking information. But for this current study, I didn't include those information. And to the right, I just wanted to give you an idea of the eta coverage. So I'm plotting the kind of a distorted detector, the tracking layer geometry of the radius versus eta, the pseudo rapidity. And you can see that a particle going to along eta equals 0 can hit 8 layers of the tracking detectors. And on the backward, which is the electron going direction, you have 5 hits. And the hadron going direction, you can have as much as 7 hits. All right, now let's talk about simulations. So the Athena collaboration decided to build a new simulation framework which take use of all those modern software available from the high energy community. And that was a brave move, I would say, because considering you have less than 1 year to develop the proposal. And there were a lot of effort from the Athena software working group to make this entire thing work. So for the simulation and geometry, we used the DT4HAP. And to the right, I just wanted to show you the level of details we put into the simulation. You can see the projective cone, which is supporting structure for the silicon trackers and also guide the cable out. And you can see those staves of the silicon barrel, and each has a triangle carbon supporting frame. All right, and then let's go to the reconstruction project, which we call it Juggler. It's a Gaudi-based digitization and reconstruction framework, and we choose to use ACTS to handle track finding and reconstruction. So we like ACTS because of its powerful combinatorial common filter, which can handle track finding and reconstruction at the same time. And so for now, we're still using the default truth seeding, and the realistic seeding with CKF is under development by a project scientist from the Berkeley Lab group. And the ACTS also allow us to simplify the detector geometries into a bunch of surfaces that allow faster reconstruction. But that also means that we need to provide a material map to match the choices of those surfaces. And with a lot of help from the ACTS expert, quarantine, and we were able to make a material map for our detector design. And to the right, I just wanted to show you that the comparison of material scan between the Gentino and what we provided to ACTS for reconstruction, and you can see they are in excellent agreement. All right, with a lot of those introductions, now I can show you some very basic tracking performance study with some single particle. And the idea is to use a distribution of single pion event at vertex is fixed at 0. And of course, we're still using a truth seeding and to look at some of the basic performance quantities such as efficiency and momentum, angle resolution, and also DCA resolution. And by looking at those quantities at each kinematics, we were able to produce some of the performance plot, like this one is DP resolution versus momentum at each eta region, at each eta or the angle theta. So this is actually a comparison between DD4HAP and some other existing simulation framework. So the it's like a benchmark to help us make sure that our simulation works. And we're happy to see that they are in general in good agreement, except at certain point at eta equals 1. If you still remember, we have the projective count. So the geometry is slightly different between different simulations. So we're not worried about this. And at a very large eta, we know that the fast simulation used a constant magnetic field, while the other two, Fun for All and our simulation used more realistic magnetic field, which will reduce at a large distance. So that explains the performance here. And then let me just quickly remind you that with the EIC detector design, we wanted to cover physics at different kinematics, low x, large x, low q square, high q square, and all those different interesting physics process put you a set of tracking requirement. So for example, the transverse DCA requirement. So because our low collision rate, we don't really have a lot of issue with multiple vertex recognition, but we still need excellent DCA, mainly for the hadron decays. And you can see that at a large, reasonably large PT, we have our simulated Athena detect performance is way below the requirement of the physics working group. And sorry, so I'm trying to move to the next slide. Okay, here you go. So it's a similar comparison plot for the momentum resolution. And you can see that at middle repetitive pseudo-rapidity, we definitely meet the agreement. But when we go to, for example, large negative eta, we don't have such a great resolution. But at that time, we can use some current information to help us with charged particle reconstruction. All right, and here are just two 2D plot of the resolution side by side, and so this is DPP and this is DCA, transverse DCA. Just wanted to point out that at a small PT, we have large eta, we have very few hits, and there are huge and multiple scattering, so that we don't have a good efficiency there. All right, so moving away from that, just a single particle tracking study, I wanted to show you some study going on towards a realistic tracking solution. So this page, I summarized some of the study from the Berkeley lab group, which we used the simulation to optimize our detector design. To the upper left, you have momentum resolution versus the detector sensor size, silicon detector sensor size, which is pixel sensor size, which is part of the earlier EIC R&D effort. And to the right, you have a scan of LGAD location and its impact on the tracking resolution. And to the lower part, you have, and this is a very interesting ongoing study, is that we have to create a reasonable layout for the sensors on the silicon disks that you can have good coverage on the small opening for which will attach to the beam pipe, and also good coverage at the edge. All right, and then in terms of the track reconstruction, there were studies to understand the real physics environment we are going to be facing in EIC. So upper plot showing you a sample of DIS event from PCR simulation, and there are some major background particles, and you can see that multiplicity seems to be under control. And then we have a lot of background study, for example, the synchrotron radiation study by Ray, which is also a postdoc from Berkeley lab group. And he looked at the impact of gold coating on the beam pipe. And you can see that it seems the gold coating can effectively block the synchrotron photons. And probably the last and most, not the last, but most important thing we need to develop is a realistic seeding. And here you can see that the efficiency from realistic seeding and truth seeding we currently have side by side. You can already see that we have kind of good performance at mid rapidity, small rapidity, and large momentum. But at the region with a large rapidity and pseudo rapidity and low momentum, because those regions traditionally are not that such a interesting for other high energy experiments. The common filter parameters are not well tuned. So basically, we're making progress here. Probably just need more time to find the best set of parameters and the algorithms we want to use for the common filter. Just one more slide towards the end. So we also have an interesting and unique problem because of this far-forward tracking system. And if you still remember previously, I mentioned that we have an angle between the electron and the proton, the hadron. And as a result, at the very far forward towards interaction point, you have a separate electron beam pipe and the hadron beam pipe. And this electron beam pipe is off-centered, and we will need, so one of the postdoc from University of Manitoba is working on developing the corresponding geometry plugins. And also he needs to figure out how to handle this sinusoidal boundary in ACTS. Also, okay, so next slide as a summary. Today I showed you that how this DT4HAP and ACTS simulation reconstruction framework has been successfully developed and benchmarked. And now that actually has been selected as a reference design, and all the detector proposal collaborations are merged, and as well as the software and simulation effort. So there is ongoing discussion on the choice of software, but I think both groups, HA and Athena, have kind of agreed that ACTS will be the choice of reconstruction. So all the effort I showed you here today is still not in vain. And so we are still working close with the ACTS group and have bi-weekly meeting with them to continue the development, such as for the realistic seeding and for the special cylinder geometry for our far-forward systems. And we are preparing for transform this effort into the formal Detector 1 framework. And I would like to end my talk with a question to the experts. So two key EIC technologies we hope to have is streaming readout and machine learning. And we were wondering if we can get some suggestions on how we can have track reconstructions, for example, with just a part of event information instead of event by event informations. And that's it. Thank you.
Thank you. Maybe we can start with questions to the experts first. An expert with an answer.
Well, let me answer. Let me first thank you that you put this talk together. I think that's really nice to see that the communities start sharing code and work together. I think that's a very good thing. So from our software design from ACTS, we do not require that full event information is available. We really try to have it all designed that you practically data driven. So what you give to the modules is processed. Yeah, that's not the case with our demonstrator examples, because there we just do simple event processing one by one. But it should not be a problem to use the same tools on partial event data. Also with timing stamps, of course, that are transparently carried through. And as for the machine learning, I may invite you to join the ACTS machine learning mailing list, where we have bi-weekly meetings, and for instance, also as one of the project have now integrated the extra track pipeline as one track finding approach that ships with the software.
Okay, great. Thanks for your answer. And definitely we will have more discussion in our future meetings.
Absolutely.
I hope I didn't put you on the spot. No.
Don't worry, don't worry.
All right. Go back
Okay,
to this work. So.
Then maybe let's go to the more usual questions. I don't see anyone on Zoom. Is there anyone in the room who has a question?
I'll give one bounce back to you guys. No. In a very good sense, I invite people who are interested also to see in what nice strategic way the EIC community has done detector design using pipelines, so CI pipelines. So they were really making it not a differentiable way of designing detectors, but every new detector layout you could push basically as a continuous integration job through the pipeline. So I think that was a quite nice way how this was done.
Yeah. I see Maurice has a question.
Yeah, hi. Maybe you said this and I missed it. I was wondering, is the detector design completely final, or is it still possible to optimize it?
Well, let me go back to this. What is the best way to say it? So we have a reference design, which is etched, and it's definitely not finalized, but this is like a, I don't know, reference, which means we will need to verify its performance and improve it. And we already know that we want to change certain things. Does that answer your question?
Yeah, right. No, so that's good. So, I mean, I guess a concept that's not sure how usually we do these detector designs, through iteratively, right? You have a reference, you simulate it, you found all the problems, and you try to make tweaks to the reference, and then you go again. a new concept would be like the co-design of the detector and the reconstruction, which, you know, there are some, for example, at this workshop, there were some presentations on, you know, how to use machine learning to optimize the detector layout and so on, you know, attempts at that. So is that something that is a possibility, or do you see the detector design as the classical iterative?
Well, first, I'm really not in the position to make any like official statement, but I remember that Edge did mention that they used machine learning for the tracking system optimization, but I have no idea exactly what they did. So for now, I don't know, so just a little bit of details. So for now, because we're still like merging different proposal collaborations into one detector collaboration, and we have the working groups are now supporting 2 simulation frames, and they are doing, I think they started to make some changes, and those changes will go to simulation as you'll see that there will be some iterations. And I think they do need to make some key decision very soon, like July or so. Yeah, but I mean, I would say the best answer I can give for you is, if you're interested in those, please join the EIC user group and attend the working group meetings.
Okay, thank you.
Any last question? Anyone in the room or on Zoom? So let us thank the speaker again.